Trig, what's happening? We're out of trig, actually. I have to call you pre-calc from now on. You're not trig anymore, but old habits die hard. We are currently talking about logarithms. So we actually started in the middle, and I showed you what a logarithm is and how to kind of manipulate and write an exponential as a logarithm. But now we want to go back, now that we have a little bit of base in that, I want to go back and see some of where that comes from and what we can do graphically from that, being able to graph an exponential and graph a logarithm. So I sent you home with a little pre-notes worksheet to try on your own, and then I thought I would just go through it with you, so now you can check and see what you wrote. Does it match what I'm saying? Is there anything you want to add? Anything you want to delete? Anything like that. So why don't you get yours out, and then we'll go through this thing together. Sound good? Good. Okay, so this is where we started. Just telling you what an exponential is. We have some base, right? That big number down there we call the base, a base of 2. We're raising it to a variable power. It can't be 1. I'm not sure we've talked about this yet, but if the base is 1, we would have 1 to some power, 1 to the first, 1 to the second, 1 to the third, 1 to the fourth. It would always be 1. We would never see any exponential growth. So we just want our base to be a positive number, not 1. So good old-fashioned, how we normally would start this thing is just make an XYT chart, make a little table. We fill it out. I'm raising 2 to the power of 2 to the 0 power, 2 to the first power, 2 to the second power. Going the other way, 2 to the negative first. Would flip it upside down. It would be 1 over 2 to the first, 1 over 2 to the second. You get the idea. I jammed it in my calculator. No big deal. And then I'm going to sketch a little graph. Noticing here, when I sketch my little graph, my x values, I could pick any x value I want. I could go to negative 100, and I can go to positive 100. But my y values never get in the negatives. So I actually don't need quadrants 3 and 4. So when I sketch my little graph, I don't need quadrants 3 and 4. I just need quadrants 1 and 2. I plot my points, and we get a graph of this thing. This is exponential growth. We saw a lot of this stuff when we were talking the COVID virus and the coronavirus and COVID-19, and exponential growth is 2 people can infect 2 people each, and those people can infect 2 people each, and so on and so forth. We see this sort of thing occurring in nature, exponential growth, exponential decay, and we'll get to that in a little bit. Okay. Next, just a little what's happening to our graph as our x values get smaller. So as I go to the left on my graph, what's happening? It's getting closer to 0, right? 0.5, a fourth, an eighth, a 64th, getting smaller and smaller and smaller. It's getting closer to 0. Well, what do we call that? We call that an asymptote. Remember, an asymptote on our graph is the worst landing ever. We get closer and closer to the runway, but we don't actually ever touch down. And the same thing happens here with this exponential. I will never actually get to 0. I'll get really, really close to it. And I definitely won't get negative values. There's no value I can plug in for x that's going to give me negative y. Okay, we call that an asymptote. So now with our little bit of vocabulary here, and we kind of already hit it, it would say the graph will get closer and closer to 0 as my x values decrease. So there is a horizontal asymptote at the line y equals 0. Horizontal lines are y equals something. Vertical lines are x equals something. Okay, moving on. What's happening the other way then? Well, we call that exponential growth. 2 reproduce to get 4, reproduce to get 16, reproduce to get bigger and bigger and bigger by some power, raising 2 to a power. We call that exponential growth. Next. What's the y-intercept? I gave you an easy one just because we're going to use it later. The y-intercept is 1. Okay. Now what I wanted to do is open up a Desmos and see, do all those questions follow for all exponentials or just the one that we just happened to graph? So let's go to Desmos, let's open a Desmos, and let's plot these things. And this is good practice for us. So I will open a Desmos. Graphing calculator version, please. I want to graph 3 to the power of, I'm going to hit 3, and then I'm going to hit Shift 6 to give me an exponent, and then I want an x there, 3 to the x. There's 3 to the x. Looks pretty darn similar to 2 to the x. Well, let's look at 2 to the x too while we're here. Okay, 3 to the x is actually going to grow faster. Instead of doubling each time, times 2, times 2, times 2, times 2, it's times 3, times 3, times 3, times 3. But everything else is the same. The domain, the range. I might have skipped domain and range. Well, that's okay. The domain goes from all the way to the left, all the way to the right. So all real numbers, negative infinity to positive infinity. And then the range, it goes from 0 to infinity, but not including 0 and definitely not including infinity. So we have parentheses around both of those. But 3 to the x and 2 to the x have very similar characteristics. The domain and range is the same. The y-intercept is the same. Growth, exponential growth going this way, asymptote going this way. They're all pretty much the same. All right. So let's look at the other one we were supposed to look at. The other one we were supposed to look at was 1/2 shift 6 to the x power. Okay, we call this one exponential decay. As I get bigger and bigger on my graph, my values are getting closer and closer to 0. This really is the worst plane ride ever. After 2 seconds, I'm 0.25. I'm almost down touchdown. After 4 seconds, I'm even closer. After 6 seconds, I'm even closer. 8 seconds, closer. I never actually touch down, though. We call this exponential decay. In your chemistry classes, you've talked about radioactive decay. As these elements just sit there, they're slowly getting smaller and smaller and smaller as these particles shoot off. We have half-life of these things. Half-life is the amount of time it would take for there to be half as much of the element that we had before. So all this is radioactive decay, and we now have the mathematical model that kind of represents that. So what questions would be different? Domain and range is the same. The domain, it goes to the left forever. This would still keep going to the left. Goes to the right forever. The range never gets in the negative, so that doesn't change. If anything, I would say as we increase, we're getting the asymptotic behavior. It's approaching 0. And as we decrease our x values, that's the exponential growth. So those two things switch when we have a 1/2. When our base is less than 1, that's what's going to happen. When our base is a half, those two things switch. Instead of exponential growth, it's exponential decay. Okay? So let's go back to our notes. I think that's what I wrote here. It is. Which questions change? 3 to the x has all the same answers. A half x, they just flip-flop which direction it's going, really. Grows exponentially as x decreases. That's when it's getting bigger. But as x approaches, or as x increases, that's where we're seeing that exponential decay. It's getting closer and closer to 0. Okay, so we have exponentials and exponential graphs. Not too bad, pretty easy. Now let's move on to logarithms and logarithmic graphs. So we have our little notes here. A logarithm and an exponential are just different languages of saying the same thing. One thing we do want to know, and if we haven't talked about this in class yet, here you go. Taking the logarithm of an exponential cancel each other out. Log base 5 of 5 to the x, that just leaves me with x. And vice versa. Raising a log to a power, so 3 to the log base 3 of x. Raising, having a logarithm as your exponent, as long as those two bases are the same, those cancel each other out. So what do we call operations that cancel each other out? We call them inverse operations. And these are inverses. A logarithm and an exponential are inverse operations. They undo each other. So all the things that happened with inverses before, when we were talking inverse sine in our trig class, and we were referencing square roots and squares, those are inverses. All that stuff is going to apply, and that's what's in this next paragraph. X's become Y's, Y's become X's. Domain becomes range, range becomes domain. So our next question just says, what would the domain and range be for a logarithm? So what we're going to do is just look at our domain and range from the exponential. This is the exponential one, and just flip them. This is now going to become the range. The range of a logarithm can be any value, from negative infinity to infinity. That's what it gets kicked out. The domain of a logarithm is only positive numbers. Because the range, this one, will only ever kick out positive numbers, that's the only type of number I'm allowed to plug into a logarithm. This is important. You can't take the logarithm of a negative value, and it's because of this idea right here. My range are only values between 0 and infinity, so that becomes the domain, the stuff that I'm plugging into my logarithm. So we switch the domain and range, and we get something like this, but we get that important little nugget there. We can't take the logarithm of negative values. Let's look at it here. The log of 2. Okay, that's fine. The log of negative 2. That's not fine. You're not allowed to do that. There's an error because you can't take the log of negative values. Okay. Next, we want to fill out the table. Well, to fill out the table, exactly what I said up here. X's become Y's and Y's become X's. I just flipped that table from earlier. So again, I look at my exponential. This was 2 to the X. Now I'm graphing log base 2 of X by switching my X's and my Y's. Okay. And then I'm going to graph it. So just like before, we can be strategic. Looking at my X's, my X values don't get in the negatives. I won't need quadrants 2 and 3. My Y values, yeah, they go down to negative infinity and they go up to positive infinity. That's our range of this thing we were just talking about. So when I graph this thing, I only need quadrants 1 and 4. And I sketch a graph of it. It is increasing. The Y's are getting bigger as I get over, just not very fast. So notice at 1, it was 1. At 2, or at 1, it was 0. At 2, it was 1. At 4, it was 2. At 8, it was 3. So these Y values are increasing. This thing is going up steadily. It's just taking a long time. I have to move my X's really, really far to get to the next one. So we have a picture of log, and we have a picture of an exponential. Let's look at it at Desmos real quick. They should be reflected over the line y equals x. That's just another property of inverses. So let's do 2 to the x. And now let's look at log. To get a base, if you ever have to do this, you hit shift and the minus sign, shift and minus, log base 2 of x. And then let's just put that line in between them. They're supposed to be reflections over the line y equals x. And they are. Perfect. And that's what happens with inverses. All the x's and y's get flip-flopped. That's what's going to happen when you do that. Moving along. What's happening to values between values of x values? What's happening to the y values when my x values are between 0 and 1? Between 0 and 1, my y values are all negative. And again, that comes from an exponential. All the exponential and logarithm stuff is connected. So when my y values are between 0 and 1 on this graph, my y values, my x values are all negative. Well, all I do is switch x and y. And that statement I just said, I'm going to switch my x with my y, and we get, okay, well, if all the x values are between 0 and 1, all my y values are negative. So anything less than 1, so half, a third, 0.621, we're going to get a negative value for my y when it gets kicked out. Okay. Last little part is just tips and tricks on how to graph a logarithm. Let's see if you did it right or did it semi-correctly. To begin with, log base 4, if I didn't have any of these other bells and whistles, it would have a vertical asymptote at 0. Okay, well, I shifted all my points, including the vertical asymptote, over by 2 to the left. So there's actually a vertical asymptote for this thing at x equals negative 2. Okay, so I'm just gonna plot that real quick. So x equals negative 2. I get my vertical asymptote. Good. Now the easy values for this. It's easy to take log base 4 of 1. That would be really easy. So I have to ask myself, what value would I have to plug in here to make this parenthesis, this argument, equal to 1? The answer is negative 1. So I'm going to plug in negative 1 into my function and see what it kicks out. So I'm going to plug in a negative 1. Negative 1 plus 2. Negative 1 plus 2 is 1. Perfect. Log base 4 of 1 is 0. 0 times negative 2 is 0. 0 minus 3, negative 3. So I get this point on my graph, negative 1, negative 3. Negative 1, 2, 3, negative 3. I'll put a dot. Okay, now we need another one. It's kind of like our tangent graphs, right? I don't know, is it going to approach it going up? Is it going to approach it going down? I know it has to get closer to this dotted line, but never touch it. So we need another point. The other point was whatever this base is. I want the argument to be 4. I want inside of here to be 4 because it's easy to take log base 4 of 4. Well, what does x need to be to make that happen? The answer, 2. If I plug in a 2 right here, I would get 2 plus 2 is 4. Log base 4 of 4 is 1. 1 times negative 2 is negative 2. And negative 2 minus 3 is negative 5. So I get another point. Negative 2, or just positive 2, negative 5. Positive 2, 1, 2, 3, 4, 5. Negative 5. You can kind of see what's going to happen. Now it has to go through this point, then approach this asymptote and never quite get there. So something like that. and then it's going to keep moving in that direction, but I ran out of paper. But that's the idea. That's what it would look like. And we could always use Desmos and check our answer. But it's nice to have this background information on where does it come from? How do I get it? Okay. So there's our notes on graphing these things. Okay. Be on the lookout for the stamp and or a worksheet to keep practicing it. As always, email me your questions, and we'll work on this stuff in class. Moving on.